Hello everyone, a warm welcome to my YouTube channel. I am Rohit, and in today's video we are going to discuss a very interesting topic. Is time an illusion, or rather what exactly is time? Now the answer to this question, which I am going to explain, is that yes, answer is that time is an illusion, and also time is not an illusion at the same time. Now this sounds really bizarre, and it doesn't make much sense once when you see it at the first sight. But it is the truth actually. Now, why and how and to understand all this, you'll have to view this video in entirety, and it will start making sense to you why exactly I'm saying that time is an illusion and also time is not an illusion at the same time. And is that even possible? How exactly it is happening? Now, this is also going to be a bit long video, and almost it's like a PPT, and almost till slide 15, 16, or maybe more. I'm going to discuss what other people say about time, or what are the other concepts of time. So the real video is going to start after slide 15 or 16. So please bear with me. This is going to be a bit long video, but I think that it is worth it, because the problem of what exactly is time, and it is a bit of a mystery still, and even top level physicists are not having any they agree, they don't have any agreement, or they disagree in their opinion about what exactly is time. So whatever I'm going to discuss today is from this book, Decoding Gravity, Time and Causality, and it describes dynamic general relativity, which is a variable speed of light type of general relativity. So VSL type of general relativity. So whatever we are going to discuss today, what exactly is time, is basically what is time as per VSL type of general relativity. Now, this VSL type of general relativity was described by Einstein in his 1911 paper. So it is not out of the blue moon. So this was already described. The mathematics of it rather is almost similar to general relativity, and Einstein had said that variable speed of light type general relativity is actually equivalent to general relativity. So this dynamic general relativity is almost equivalent to general relativity. So that is what we are going to discuss today. So anyhow, so what is time? Time is the definition of time. It's a mystery actually, because a lot of controversy has been created because of it. So for a lay person, time is what? It's a relentless march forward of the hands of the clock. So whatever clock which we are owning, they keep moving forwards, and that's what is time. And that's the typical layman definition of time. And typical logic of a person, lay person, non-physicist, would say that there is a definite present which is distinctly different from past and future. Past has already happened and gone, cannot be accessed. Future is unwritten, exists only as possibilities and can be changed. So that is what is the typical logical definition of time. So the time, according to proper logic, according to logic, it has a definite arrow of time from past to present to future, and only present exists. So future doesn't exist and past has already gone. So neither future nor the past exist. Only the present exists. This is what logic says. So logic also would say that there is an absolute time, that there is a universal clock somewhere, and that ticks for everybody at the same pace. So there is a universal clock somewhere, and so at every point, this universal clock ticks at the same rate or the same pace. So there is universal simultaneity, and there is no time travel. So all this is basically typical logic, what logic says about time. Okay, but we know that this is wrong. Basically, we'll come to that why. So there is something called as realism. What is realism? Realism is a philosophy basically. So in this philosophy of realism, what is time? In realism, the universe exists irrespective of conscious observer observing it. So it's basically that the universe is real. So it's not an illusion. So the moon does exist. So the particles of the moon does exist, irrespective of whether you are looking at it or not. And the particles of the sun and the particles of the Milky Way and all that, this whole universe, it might look different to us, and it might look different to the radio telescope or an infrared telescope, but it is still there. It is real, and there is something which is there in the location of the sun, which is burning or which is undergoing fission or fusion. And so all the particles of the universe have a definite position and a definite and at each moment of time they have different position, and they have definable time. So every particle has a definable time. So that is what realism says. So realism, what it says is what? That there's no superposition. So the electron cannot go from one slit two slits at the same time. So it has to go from one slit. So if the electron is there, it is a particle. So if the particle is there, it has a specific location. So if it has a specific location, it cannot pass from two slits at the same time. So there is no superposition. So at one small moment in time, the particle will have a specific location. So all this is realism. We don't know that realism is true or not, but that's what realism would say. So in realism, what is time? In realism, there cannot be any uncertainty. So there cannot be any uncertainty in existence, any uncertainty in location or path or any events. So there cannot be the electron cannot pass into from one point to the other point by multiple paths. So it cannot remain as a cloud. It has to have a very particular location. The location may change at an extremely rapid rate, like sub-Planck time intervals of time. It can change, but it still has a definite position at a one particular given time interval. So this existence and location and path and events. So even events, there are two events, especially contradictory events, cannot happen at the same time. So two opposite events cannot happen simultaneously. So there cannot be a superposition of a dead and an alive cat. So that is what is realism. So realism says what? If the electron is there at one particular position, it is there. So it cannot be at 10 positions at the same time. And if the electron is a right spin, then it has to be only right spin. If it is a left spin, it has to be only left spin. So there cannot be a superposition of a right and a left spin electron in realism. So this is what realism says. So what does realism say about time? Even in realism, time would be absolute time. So there won't be a relative time. So relativity has a bit of a problem with realism. So realism and relativity, and even realism and quantum mechanics, both are in loggerheads. So it's a bit of a mystery that realism is what our logically it seems very proper, but physics and experiments say that realism is not right. So the time of realism is also not right. So it's not absolute. Okay, so what does Newtonian mechanics say? It says that time is absolute and universal simultaneity is there, and there is an infinite speed of exchange of information or causality. So that's what time in Newtonian mechanics says. What about time in special relativity and general relativity? Now, this is where the contradictions started, because before Einstein came into picture, everything was fine about time. Nobody even discussed about time, because everyone knew that time is absolute and that there is universal simultaneity, and that that there is no question to be asked about time. But once special relativity came, everything changed. Einstein um, suggested that the universe could be block universe, and that the entire the universe, the rather time is really an illusion, because every person can have a personal time or a different time. So every particle can have a different time. So one particle can have time running much faster, and the other particle can have a time running much slower. So if a particle is moving with the speed of light, time effectively stops for that particle. If the particle is moving with a very extremely high speed, then the time gets extremely dilated for that person. So in that time, there's no universal simultaneity, and that there is no past, present, or future, and that there is a limit to causality, that is the speed of exchange of information. It can happen only with speed of light. So all these things are what special relativity or general relativity says about time. Now, all this seems counterintuitive, but this is true. It has been proved pretty obviously, so you cannot completely brush it under the carpet. So we know that GPS, general relativity and special relativity, the gravitational time dilation caused by predicted by general relativity, and velocity time dilation predicted by special relativity, both are true, and the effects of them cannot be neglected completely. Otherwise, our GPS would um, show gross errors. So those errors have to be modified with the help of the changes in the time because of gravitational time dilation and velocity time dilation. So both of them are tested by thousands of experiments. So special relativity says that there is no universal simultaneity. Okay. So what exactly is time? So it can run at different pace at different points, and potentially has it. There can be infinite different velocities of forward progression of time. So one particular particle has a much faster progression of time than the other particle, and so on. Okay, so time, there is past, present, and future exist independent of each other and already determined. So that's what the future is already determined by the past, and that it cannot change. Past of one can be future of the other, because past cannot be changed. Future of everyone is already predetermined. So the present of a person, it all depends on the pace of its personal time. So if a particular person has a time which is moving very slowly, and the other person has a time which is moving very rapidly, so then there one particular person whose his past may be the future of the other person. So in that sense, um, uh, So basically, that is the reason why time is like a block universe. That is, past and future all exist at the same time simultaneously, and that there is that that so every person's present is a slice in the block time, and that the so different people have a different direction of slice. So that's what is said by special relativity and general relativity. So in special relativity, time is married to space to form space-time. This depends on status of space. Also depends on velocity of a particle. So what about quantum mechanics? So here we have already got enough confused basically. Now quantum mechanics comes into picture, and quantum mechanics says that no, time is not relative; it's absolute. So there is the time is just a background entity which cannot dilate. It doesn't change with space. It is not married to space. It has independent existence, and it is just a background entity. So here quantum mechanics and general relativity are in loggerheads. So they just are incompatible with each other. So special relativity says that there is no universal simultaneity. Quantum mechanics says that there is universal simultaneity. There is one time and that goes forward. So it's an absolute time. So what exactly is true? Whether quantum mechanics is true or general relativity is true, nobody knows. Okay. So here again the marriage between the space and time. Space and time are independent in quantum mechanics. In general relativity, they are married to each other. So in LQG or loop quantum gravity, time disappears, and it's a very vague thing actually, that it either doesn't exist or it exists only as an interaction of particles with spin foam that creates time. So which is a very vague thing, vague definition of time. So in LQG, time is actually not there at all. So it's not only an illusion, but it just disappeared from the equations of loop quantum gravity. So it's like now we come to dynamic general relativity or variable speed of light type of general relativity. What does it say about time? It says that there are two times actually, two different types of time. One time is the real time, and the other type is the illusionary time. The illusionary time is just illusion, so we can see it or we can measure it, but it is unreal. So that is an illusion. So it is okay. So the real time is absolute time, which is the time of quantum mechanics or realism or non-Newtonian mechanics. So it's called as the universal time. Local time is what? It's the time in general relativity or the relative time or okay. So local time and universal time. So these are the two times in dynamic general relativity. The local time is an illusionary time. So local time can dilate or contract due to active spatial expansion or contraction. So local time is the one which is intricately married to space, and the only time we can detect is the local time. So all the experiments which we do, all the things which we measure, the clocks which are measuring time, the millions and billions of clocks which are there on the surface of the earth, including the atomic clocks, they can measure only local time. They cannot measure universal time because dynamic general relativity says that there is active spatial contraction happening because of the gravity. And this active spatial contraction we cannot see, nobody can see it, but it's there. It's all throughout, and it is much more nearer the surface than far. So the nearer the surface, active spatial contraction is much more. The as we go further out apart, active spatial contraction is much less. So local time is varying nearer the surface. But what about the universal time? So local time is the illusionary time. So there has to be some real time in it. So there is a time which is the real time, which is the Relativity has described something called as t is equal to 0. T0, that is time of an object which is infinite at an infinite distance from from any gravitational body. So it's actually it's a difficult thing to measure experimentally, because we cannot have infinite distances from any gravitational body. So if you go from the Earth away from the Earth, infinite distance away from the Earth, then you will come closer to other gravitational bodies. So you cannot have a body which is infinite distance from the. So experimentally, it is very difficult to measure universal time, but this universal time is still there according to dynamic general relativity, and that when we are doing experiments, we cannot completely negate the active spatial contraction which is happening because of the gravity, and that's why the only time which we can measure is the time dilation which we are able to see is an absolute error. It is not real time which we are measuring. The real time is a universal time. So the illusionary time of the local time is the only time which we are able to measure. Now I'm going to discuss a bit. So this is again another diagram, the same diagram which I used when I was describing variable speed of light, or is light velocity constant or variable, in my previous video. So you can go and check out that video before to know more about this particular diagram. But imagine that this is the circle in the center is the Earth, and C is the center of the Earth, and you can just at any particular random distance from the center of the Earth, you take a spherical space, volume of space between two spheres. So think about P and Q. PQ is one particular line, and P dash Q dash is another line, and P dash dash Q dash dash is another line. So general relativity says that because of the mass of the Earth, a spherical space-time wave, space-time deformation wave starts from here, goes at the speed of light and reaches PQ, P dash Q dash, P dash dash Q dash dash, all of them. And what happens is that the space in between P and Q contracts. P dash and Q dash also contract, and P dash dash Q dash dash also contracts. So this particular wave, as soon as it reaches the space contracts. So this particular sphere, so if you can say there are n number of these arcs, PQ, P dash Q dash, P dash dash Q dash dash, P dash 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 Q dash dash, like that, n number of arches are there, and each of these arches will have one wave. So the first wave and the second wave, then third wave, like that, they keep forming over here, deformation waves. Space-time deformation waves are starting, and they are reaching here. So once they reach the sphere, what happens is that the sphere contracts because PQ contracts. So P dash Q dash also contracts. P dash dash Q dash dash also contracts. So the overall sphere will lose its surface area, and it will lose its radius. So this particular space will move inwards, and it will form a new sphere. So this new sphere will have a smaller radius, but this smaller radius new sphere will again be under the influence of the second wave. So the second wave will again deform this, and it will lose further space. So essentially what is happening is that this whole sphere is moving inwards, and it is forming a newer sphere every interaction. With every space-time deformation, the sphere goes down, goes inside. Now, this is what I'm not talking about dynamic general relativity. So this is general relativity typically. But this is not what is taught actually, because this is basically variable speed of light type of general relativity. How? I will explain to you. So think of it like a pendulum. A pendulum, imagine that there's a pendulum which is made up of iron or so any ferromagnetic material, and it is you can measure 1 second by this particular pendulum. So you can do experiments on it. But think of it that I have rigged the pendulum so that I have kept electromagnets at the other ends or two ends of the pendulum, so that when the pendulum is rigged, what will happen is, okay, so when the pendulum is not rigged, let's say that there are 20 oscillations per second. So when the pendulum finishes 20 oscillations, we know that there is 1 second has passed. So here, what happens is that if we start the electromagnet, then what is happening is that the electromagnet will keep pulling them together. So what is happening is that every time when the pendulum reaches L, this left electromagnet starts and it keeps pulling, and then when it reaches R, this right electromagnet starts and it starts pulling. So essentially what is happening is that the pendulum gets rigged. That is the frequency of oscillation of the pendulum is reduced. So initially we thought that 20 oscillations of this pendulum will be 1 second, but here 20 oscillations of this pendulum will be much more than 1 second. But if we don't know the rigged nature of the system, then we will think that the time is dilated. This pendulum will we will never be able to know that the time it's basically rigged. So in the similar manner, think of it, consider this photon clock. So there is a left mirror and there is a right mirror, and there is a photon bouncing from left to right, then left to right, left to right, like that. Now, if this is a non-rigged system, that is there is no active spatial expansion or contraction, then one particular frequency of oscillation of this photon will be there. Okay, so the photon has to travel with the speed of light. So the speed of light will be maintained. But if there is an active spatial expansion of the just behind the photon, then what will happen is that the photon will be pushed to the right. It will be pushed to the right. So it will reach R faster. Then again, when it is moving from right to left, then again, just behind the photon, there will be again active spatial expansion. So this photon will be pushed to left faster. It will basically travel faster than the speed of light. So even though the photon is traveling one Planck length in one Planck time, the active spatial expansion is basically causing the photon to move forward at a speed which is faster than this. How this happens, you will be able to understand in the video variable speed of light. So variable speed of light, because of active spatial expansion or contraction, is actually not violating special relativity. So special relativity, this photon is basically traveling forwards one Planck length in one Planck time, but the spatial expansion just behind it is pushing it. It's like standing on the escalator. So this particular photon wants to walk one step at a time, but the escalator itself is moving much faster, so it has to anyhow travel much faster than that. So this photon, if its velocity increases, what happens is that it can reach the right and the left mirrors faster. So the ticking of this photon clock will be faster. So it will measure time more quickly. That is, the pace of its ticking or the frequency of its ticking will be faster, which means what? the time will be shown as contracted time. So if there is active spatial expansion, the place where there is active spatial expansion, the photon clock will show an erroneously faster ticking. So it's basically an absolute error. So you cannot make out, because this active spatial expansion or active spatial contraction which is happening, you cannot detect it experimentally. So it's an absolute error. So whenever there is actively expanding space behind the photon in the photon clock, the photon clock ticks faster. So wherever there is space is actively expanding, there is time contraction. Again, the same thing, if there is a active spatial contraction just behind the photon is moving in this direction. There is a active spatial contraction here rather than expansion. So this contraction will pull the photon. So its forward progression will be hindered actually. So its velocity will be reduced. So if its velocity is reduced, what happens is that it cannot reach the right mirror at the same pace. So it will basically, its ticking will slow down. If its ticking slows down, that means what? It will measure a dilated time, or it will if you are keeping three photon clocks at three and you compare them, the upper photon clock is basically having an expanded space time, and the middle clock there is no expansion or contraction. The lower down clock will have a contracted spatial time, or actively contracting space behind the photon. And what will happen is the middle one will tick at one particular pace, but that same pace, the upper and the lower will not tick. The upper one, which has active spatial expansion, will tick much faster, and the lower one, which has active spatial contraction, will tick much slower. So that time in that it will measure a dilated time. So wherever there is active spatial contraction behind the photon clock, it causes the photon clock to tick slower, and wherever there is actively contracting space, there is time dilation. So you can just see this particular image. It is showing. Imagine that this is a train of photons. So this is a photon. This is a photon. This is a photon. So they are basically entangled photons, and they are traveling with a particular velocity, which is the velocity of the light, or the c. So imagine that there is no active spatial expansion or contraction here. So what happens is that all of them are moving with a uniform velocity. So imagine that this particular thing is the direction of the propagation. So this is, they are moving in the from this direction to this direction. Okay, they are moving in this direction. Now we have to, so this particular scale is given for reference. Okay, so in 1 second they move from here to here, and then the next second they move from here to here. You can imagine these as photons, or you can imagine this as a wave front of a wave of light. So this is a wave front of the wave of light. You can think of it as you can forget that there is a photon over here. You can think of it as a wave front of light also, or you can think of it as a entangled photons also. So after the first second, the position is this. After the second, the position is this. After the third second, it will be like this. It will be like that. So the distance which is covered by them is almost going to be the same. Now, what happens if there is a variable speed of light, or there is active spatial? There is a, so if you imagine that this is a particular the same train of photons, or the same group of photons, and imagine that there is a variable active spatial contraction, but the active spatial contraction is much more over here and much less over here. So there is a much more active spatial contraction. So the extent of spatial contraction here in the lower part is much more in the extent of active spatial contraction reduces as we go away. This is typically going to happen if there is a gravitationally attractive body over here. Maybe you can think of this as a galaxy, or you can think of this as a the sun, or maybe a central supermassive black hole just beyond the event horizon of a black hole. So what exactly is happening here is what that because there is a central supermassive black hole over here, what is happening is that there is active spatial contraction over here, because it's all sucking. So dynamic general relativity says that a black hole, or for that matter, any any particle with mass. So the particle of with which sun is made up of, or particles which Earth is made up of, all of them have positive energy, and positive energy is active destruction. So there's destruction going on at the core of every particle. So even the black hole, there is a huge amount of destruction happening at the center. So because the destruction is happening, there is a void formation. So the void formation keeps sucking space-time around. So there is an active spatial contraction. So here in the lower part, there is much more active spatial contraction. In the upper part, the spatial contraction reduces. So what is happening here is that the lower photon will have a much less forward progression velocity. The upper photon will have a much higher forward progression velocity, because the rigging here is much more than the rigging over here. So there is an active spatial expansion here, contraction. There is active spatial contraction here, everywhere. But the active spatial contraction is much more over here than here. So this will, in 1 second, it will move forwards to a much lesser distance. This will move forward much lesser distance. This will move forward much more, because there is less active spatial contraction here, because the distance from the black hole is much more. So in a sense, what is happening is how because of the active spatial contraction, what is happening is that different photons are traveling in with different velocities. So here the photon is traveling much faster than here because of the active spatial contraction. So there is a gradient basically. So there is much more active spatial contraction here, much less here. So there is a gradient basically. So so you can see that the direction of the wavefront has changed actually towards the gravitationally attractive body, which is actually nothing but gravitational lensing. So this is how a variable speed of light type of general relativity explains gravitational lensing. Now think of it like this. So here in the lower part is the gravitationally attractive body. Let's say the central supermassive black hole, or maybe the star. Okay. So think of this particular cubical space. Think of it that there are multiple layers: layer A, layer B, layer C, layer K, layer L. Now you understand that it is almost impossible for us to mark these or name these as A, B, C, D. Imagine that there are hundreds of birds, and they are all alike. Basically, they are all alike. They are pigeons, and out of them, one of them is your pet, and he is also part of the flock. And he comes to you, and he sits on your shoulder. But you know that after some days he is going to again go away. So how to know the whereabouts of that particular pet of yours? So you can put a RFID, tag onto this thing, so that when the bird flies away into the flock, then you can detect that particular bird. So the detection of that particular bird, and you can actually detect where the bird is, and you can actually detect where the flock is going, how it is moving, and all that. So this basically marking we can do with birds, but with the layers of space or space time, it's very, very difficult to do. So in principle, experimentally you're going to do this, but still, if we imagine that if this was possible, if this space time layers where we could mark them or we could name them. So this particular cube, what exactly happens to this cube, with one layer A, second layer B, third layer C, and last layer K and L. So if there is active spatial contraction here, this L goes down, then K goes down, then like that A goes down, B goes down, C goes down. So there is a active spatial contraction at each and every of these layers, but L has much less active spatial contraction, much more active spatial contraction, and A has much less active spatial contraction. So the horizontal length of L will keep reducing. For all of them it is true, but it is much more for L at any point than A, right? So here L will start reducing. So actually this L is like PQ actually. So L represents one particular height. So at this particular height, there can be a circle or a sphere all around the particular central supermassive black hole. So this L or this particular length of L represents PQ. So if this PQ or if this L reduces, then it will basically reduce the surface area or the circumference of the sphere, which whose part L represents. So if the circumference reduces or the surface area reduces, then what happens is L the radius reduces. So the L moves downward. So if the L will move downward, K will also move downward. Then A will also move, C will also move, B will also move, B. So they keep moving downwards. So eventually, what will happen is A, B, C, K, L will from here they will move to here, then they will move to here, then they will move to here. Like that, they will keep moving downwards. So if there is an apple over here, the apple will also keep moving downwards, downwards, downwards till it reaches the surface of the central supermassive black hole. That is the event horizon. Anyhow, so if you know that this A has an active spatial contraction and also L has an active spatial contraction. So if in this particular surface, in this particular volume of space, we put a photon clock and another photon clock here. So there is less active spatial contraction here. So there will be less time dilation over here. So the photon clock will not tick. It will tick much faster here and it will tick much slower here because there is more time dilation over here, because there is more active spatial contraction over here. As they move down, the photon clock will also move down. So if the photon clock on the A will have a much more active spatial contraction, so it will start dilating as it moves downwards. So if we have marked these particular portions of space-time, and as they move down, we will realize that A will all of these will keep moving downwards. So eventually these ABC KL will move down, and then again move down, and then again move down, ultimately reach the surface. So what is the implication of all this? That variable speed of light due to active spatial contraction can explain the falling apple. It can also explain gravitational lensing, and it can also explain gravitational time dilation. So why do we measure constant speed of light? If we see that the speed of light is variable, then why do we measure constant speed of light? This is because of the perpetual error due to ever-present active spatial contraction due to Earth's gravity. So we can measure only local time. So we cannot measure universal time. So whenever we are measuring the velocity, not only we are measuring not only we are measuring local time, so local time will vary according to the location, and also so we are basically measuring local time. So if you are able to measure universal time, then we will know that the velocity differs. So the velocity basically differs based on universal time and not based on local time. So if you see, if you utilize universal time instead of local time, then the velocity will differ. So I think that this is a bit of a controversial thing, but I feel that dynamic general relativity is such a theory which is actually absolutely equivalent with variable speed of light type of general relativity, which was described by Einstein. So I think that it should be taken seriously, and it's a very high chance that it is true. So I want you people to contact me on this particular email address, or you can send a direct message on Twitter at this particular Twitter handle. You can access this particular book, Decoding Gravity, Time and Causality, on Amazon.com or Amazon.uk, or maybe notionpress.com if you are in India. But what I would say is that it's time that physicists start taking this particular theory seriously, because it's just that it's written by some non-physicist doesn't mean anything. I think it's time that physicists give up their arrogance, or maybe this thing that a physicist, non-physicist cannot write a book. So I think that they should open up their mind, and they should start thinking about this, because if a theory is there which is absolutely consistent with variable speed of light type of general relativity, which is already described by Einstein, and it can explain Newtonian gravity, it can explain MOND, it can explain quantum mechanics, it can reconcile quantum mechanics and general relativity, it can offer a theory which is a bridging theory between loop quantum gravity and string theory. So there are too many advantages for this particular theory. For the unfortunate reality is that this theory, almost 6 months have passed since the book has been published, and not a single physicist is working on this. There is not a single paper which is published, and today's today's um, peer review process is such a thing that a non-physicist can never think of publishing any paper. So there's no question that I can publish any papers on this particular dynamic general relativity. So I will request that physicists read about the book, and listen to all my other videos, and thank you very much for your time, and I think that I'll see you soon. Thank you. Bye.